In this video, we present FreeLSD, a framework for prior-free visual landing site detection for autonomous planes. Unmanned aircrafts need to be able to autonomously detect a suitable landing spot, for instance in the case of an emergency situation during a beyond visual line of sight mission. In this work, we take into account the size and texture of the landing site, hazards within and occluding the region of interest, the estimated wind direction and magnitude, as well as UAV dynamics. To keep the complexity manageable, the framework is split into a front-end and back-end. First, the results from a semi-synthetic dataset are presented. The bottom row shows the output of the front-end that segments, classifies and tracks the regions of interest. Only the most promising landing sites are forwarded periodically to the back-end. Based on the camera pose priors, feature tracks and observations, the most promising landing site is reconstructed using keyframe-based bundle adjustment in combination with planar rectification and stereo block matching. The distance to hazard map defines the safest touchdown point. The linear approach and loiter down path are checked for collisions based on a 2.5D elevation map. Next, the framework is evaluated on a dataset that was recorded by the UAV platform TechPod in a snow-covered landscape. The front end extracts homogeneous regions based on a canny edge detector and distance transform. A binary random forest classifier uses color and texture features to discriminate between grass and non-grass regions. The region manager is able to geometrically track and rediscover homogeneous regions. After every reobservation, location, size, classification result and score of the region of interest is updated. For the most promising landing spot, the segmented observations, camera pose priors and feature tracks are forwarded to the back end for 3D dense reconstruction. The 3D point cloud is converted to a grid-based 2.5D elevation map via KD tree and inverse distance weighting. Based on this 2.5D elevation map, the slope and roughness within the region of interest are computed. In the next step, the hazards are turned into binary maps based on user-defined thresholds. The hazards are efficiently fused with a logical OR operator, and for every cell, the distance to the next hazard is computed. The cell with the highest distance to the next hazard is selected as touchdown point if the linear and loiter down approach path are feasible while taking into account the wind, UAV dynamics and elevation map.